recording. This is our lecture on the properties of liquids. We're going to spend about 2 lectures on this topic, and then we'll spend another lecture talking about solids. Our final topic of the semester after that will be solutions. As I said, the idea here is that now that we have this repertoire of ideas and theories about the way matter behaves at the atomic and molecular level, with that understanding, we can now focus on the properties of matter in the macroscopic world and explain them, and sometimes even predict them if we know what the molecular properties are. So that is what we're going to be talking about. If you don't mind going to your PowerPoint notes, that would be great. We're going to be working here off of Unit 11. And this is going to span several chapters. And in the new edition of TRO, I think we're going to be now in, I don't know, I want to say chapter 12, I think, 12 and 13 maybe of the book. You'll have to go back and check it, okay? So let's go ahead and begin our topic here. So talking about the properties of the 3 phases of matter, let's start with where we started back at the beginning, which is the physical states of matter. As we observe the world around us, we realize that we rarely ever observe a substance all by itself. Many times, actually, you observe substances in the middle of other things. So when we speak of a phase, we mean the homogeneous part of a system that is in contact with other parts of the system, but separated by a well-defined boundary. So let's say you're sipping on a nice, cool, strawberry lemonade, and we see water here in 2 phases. We see the liquid phase, and we see the solid phase, the water and the ice. And many times we see matter in nature this way. We see multiple phases of it defined by a boundary. All right. The properties of the 3 different physical states or phases of matter, and we typically use the word phase when we're looking at a system that is, like I said, in contact with other parts but in different physical states. We refer to each physical state as a phase of the system. So if we look at gas, liquid, and solid, which are the 3 physical states that we've talked about, you can see here on this chart the differences in density, shape, and of course, when we say definite, means that the substance keeps its shape when it's placed in a container. Indefinite would mean that it takes the shape of the container. We see that for gases and liquids. Volume, of course, we know this from before, that liquids, although they have indefinite shape, they have a definite volume. Gases have an indefinite shape and an indefinite volume. They will expand or compress to fill up whatever container they're in. The subject we're going to be dealing with today is intermolecular forces. And we're going to see that relative to the overall kinetic energy of the particles in the system, the intermolecular forces, the attraction between different molecules, not within the atoms in a molecule, but within one molecule and another one, you can see how they are weak for gases, moderate for liquids, and strong for solids. And we can see how, therefore, the physical state of matter is influenced and maybe even determined by the strength of these intermolecular forces. Let's start out by talking about what are some of the types of motion that the molecules or atoms in a substance can have. There are several types of motion, and we call these the degrees of freedom. We have the translational freedom, which is the ability to move from one position to another. We have rotational degree of freedom, which is the ability to reorient the particle's direction in space. It'd be kind of like spinning around. And vibrational freedom would be the ability to oscillate about a particular point in space. We mentioned that sometimes chemical bonds, for example, have a bit of a spring action to them. And in the same way, molecules might interact with each other, but they may have a little bit where they come a little closer, a little farther away, kind of like a spring action. Let's bring in our friend kinetic molecular theory. We proposed this theory back when we studied the properties of gases, but we can actually expand it a little bit to the physical states of liquids and solids. We're going to say that the physical state depends on two major factors. One, the amount of kinetic energy the particles possess. The more kinetic energy, obviously, the more freedom they have to move away from each other. And secondly, the strength of attraction between the particles, which would be what draws them together. So whereas the amount of kinetic energy would tend to move them just statistically farther away from each other, the strength of attraction brings them together. And these two factors are going to be in competition with each other. And we're going to see it at play when we explain the properties of gases, solids, and liquids in the context of this kinetic molecular theory. So let's look at a gas, liquid, and a solid. And the diagrams here illustrate a little bit of what is happening at the molecular level with each one of them. Start out with the gases. We can see, based on the drawing, that gas particles are going to be in constant rapid motion. So that means they have high kinetic energy. We know from the kinetic molecular model that there is little or no attraction forces between the particles in a gas. And I'm talking under normal conditions. We've talked about how at very, very high pressures or extremely low temperatures, these somewhat insignificant attraction forces actually become significant. And last but not least, because the particles are so dispersed, the density is very low. The shape and volume are very indefinite because the particles can move anywhere in a container and fill it up regardless of its shape or size. And any sample of this substance will contain very few particles, so it'll have a low density. Okay, let's look at solids on the other end of the spectrum. Again, we can see by the fixed order of the particles in here, number one, that they're going to have very low kinetic energy. They have very little room for moving around, little wiggle room for them to move around, and so their kinetic energy is going to be low. At the same time, the fact that they're held together so strongly and almost statically means they have strong attraction forces. And any sample of the substance will contain a lot of particles, so it'll have a high density. And for the reason of them having very strong attraction forces and being almost fixed in place, they are not going to move out of their positions to change shape with the container or try to fill up a container that has a volume greater than the volume of the substance sample. The third physical state is the liquid state. And I guess from a practical point of view, we could say that the liquid is somewhere intermediate between gases and solids. There's an intermediate amount of kinetic energy. The particles can move, but not as fast nor as far as gas molecules can. There is going to be some kind of attraction forces between the particles, but it'll be intermediate between the strong attraction forces of a solid and the almost non-existent attraction forces of the gas. And similarly, in terms of density and volume and shape, it'll be intermediate. They'll have a definite volume because they don't move out of contact, too far out of contact from each other, but they can slide past each other and kind of move around to fill up a container of, whatever shape they can fit in. So when we consider the ability of these different particles to move in the different states, we can consider the degrees of freedom for each one of these. Remember, we talked about the translational degree of freedom, rotational or spinning, vibrational or the kind of spring action. And we can see that for the gas state, molecules will possess all three kinds of motion. Liquids will have vibrational freedom, but they'll have limited translational and rotational freedom. Solids will have vibrational freedom, and as a matter of fact, if we could look at the particles, let's say in a crystal, at the atomic level, there is a little bit of like a little vibration around, a little, jiggling around. But there's no translational or rotational freedom in the case of a solid. The important thing about physical states is that, as we spoke in the first week of classes, you can convert a substance between one physical state and the other one. And again, because we are talking here about sometimes a substance being in close proximity to a different physical state of the same substance, we sometimes call the transitions between physical states phase changes. And you remember this picture we had at the beginning. These are the phase changes of water between solid or ice, liquid, or what we call water, and gas, which is vapor. And the names of those transitions, which you should know by now. What is the name of the transition from, let's say, solid to liquid versus solid to gas, or let's say liquid to gas versus gas to liquid? You should know those words. That is part of your chemical vocabulary, right? Now, how do we achieve these physical state transitions, these phase changes? Well, I think for the most part, we have been familiar with the application of heat or the removal of heat to generate these changes, right? So we're familiar, for example, with heating a solid to cause it to melt, or cooling a liquid to cause it to freeze here on the left side. Or we're accustomed to perhaps, heating a liquid to cause it to boil or vaporize, right? So we're accustomed to applying heat or to cool the vapor to cause it to condense. But interestingly, as we'll see later in probably in our next class, you can achieve the phase change between liquids and gases by manipulating the pressure rather than the temperature. And that'll be an interesting discussion we will have then. Okay, so what is the nature of these intermolecular forces that seem to hold solid substances in such a tight packed arrangement, liquid substances in a semi-tight but allowed to slide past each other type of arrangement, and seem to be essentially non-existent in the gases? So these are what we call intermolecular forces. Let's start out by describing a little bit about these, and then we're going to classify them, okay? So first of all, let's consider that when we spoke about bonding enthalpies, like covalent bonds, ionic bonds, we would classify those as intramolecular forces. These are the forces that hold atoms together in a molecule, or let's say in the case of a crystal lattice, between the ions in an ionic solid, right? These are going to be called intramolecular forces. When we say intermolecular forces, we are referring to attractive forces between molecules. In other words, between one molecule and another molecule. So if we compare these two types of forces, for example, let's say, what does it take to vaporize 1 mole of water molecules into gas? It takes about 41 kilojoules of energy. Now, what if we try to break the actual hydrogen-oxygen bonds in a mole of molecules of water? Well, that would take 930 kilojoules. So you can see where the intramolecular force is a lot stronger and requires more energy to break covalent bonds than the intermolecular forces, or the energy required to simply pull apart molecules of a substance in order to, let's say, for example, vaporize them. So One important thing emerges from this, Wakanda forever. Intermolecular forces are much weaker than intramolecular forces. Or don't forget that. Intermolecular forces are typically much weaker than intramolecular forces. Pulling molecules away from each other typically costs less energy than trying to break the covalent bonds inside those molecules. So let's make a list here of what are some of the intermolecular forces. Let's start out here with a list, and then we'll go and discuss them one by one. The first one is called dipole forces. These are, again, weak forces, strengths of the order of about 4 kilojoules per mole. The second type is London dispersion forces. These are also weak forces in the range of about 2 to 10 kilojoules per mole. But what's interesting about these forces is that they tend to increase with the molecular size and the molecular surface area. So they are variable. Hydrogen bonds, on the other hand, can be quite strong with energies in the 40 kilojoules per mole range. This is the type of force that is involved in holding water molecules together in the liquid state. And therefore, that's why the heat to vaporize a mole of molecules of water is in this range of the 40-something kilojoule per mole. There is a fourth type called the ion dipole forces, but we're going to discuss these in the next unit. All right. Let's start out by looking at the molecules of water. Remember that if we draw the structure of water, either as a Lewis structure or as a Vesper structure with its proper bent kind of shape, you remember that we said that because of the electronegativity of the oxygen in here, the hydrogen-oxygen bonds are polar with a partially negative charge on the oxygen atoms and partially positive charges on the hydrogen atoms, right? Now, also because of the bent shape of the molecule and creating this non-symmetric distribution of these polar covalent bonds, the water molecule as a whole has a net dipole. So we would say that the water molecule is a dipole. And this introduces us to the concept of dipole-dipole forces. So if each water molecule is a dipole, it means that it has one end of the electron cloud in that molecule that is partially positive, and another end of that electron cloud that is partially negative, right? So if I put them together, like in a typical sample of a substance with zillions of molecules, what will happen is that the positive and negative ends of those polar molecules are going to be attracted. This is the type of force that we call dipole-dipole force. Again, it is a weak force when you compare it to the covalent bonds that are holding the molecules together intramolecularly. But in terms of the interaction with other molecules, it's a relatively weak force. But again, remember that in a sample of a substance, you have zillions of molecules, and all of these interactions are going to add up. So that means that if I look at the structure of a compound, and from its formula, I can derive a Lewis structure that leads me into a Vesper application, and therefore the shape and the polarity, I can decide if this particular compound will be capable of engaging in dipole-dipole forces. Because if the molecules that make up that compound are polar, then that means they're going to be capable of these weak dipole-dipole forces with each other. Now, what if the substance is made of nonpolar molecules? Can they still interact? Well, it's interesting, but in the 1930s, Fritz London discovered these so-called dispersion forces. And these are forces that all molecules, regardless of structure, can experience. So a substance may not be able to experience dipole-dipole forces because it's not made of polar molecules, but it can still engage in these London dispersion forces. Now let's see if we can explain it. Look at the diagrams in the bottom here. Starting with A. Let's assume that you start out with a spherical distribution of the electron clouds of the molecule. Again, this is just a picture. Remember that we cannot pinpoint locations of atoms, and depending on the theory we talk about, the locations of electrons, and depending on the theory, these electrons could be being shared in overlapping orbitals, or they could be delocalized over molecular orbitals. Now, statistically, we know that electrons are not going to be sitting still. They're oscillating back and forth between the so-called boundaries of these orbitals. And so, by sheer probability, at any instant, that electron cloud might kind of like get distorted, like we see in B. It may become temporarily non-symmetrical, which results in a temporary polarity, a temporary dipole. And when that molecule is near another one, it kind of induces that other molecule to also form a temporary dipole. This is not a static type of thing, it's a very dynamic thing. Over the range, the span of zillions of molecules in a sample, you may have these temporary dipoles, these distortions of the electron clouds happening constantly. And so what could happen is that you would have this propagation of these temporary dipoles interacting with each other in a weak form, and this is what we call London dispersion forces. Now, it turns out that although on a molecule-to-molecule basis, London dispersion forces are very weak, they have an interesting property. Because they uh, depend on the distortion of the electron clouds around the atoms in the molecules, well, it turns out that a bigger molecule with a bigger distribution of electron clouds could get distorted more readily. Let's look at this sample here, where we have samples of three known halogens, chlorine, bromine, and iodine. Remember that all three of these elements exist naturally as diatomic molecules. By definition, because both atoms are the same, they form a nonpolar covalent bond. Both atoms are pulling the electrons with the same kind of force, the same electronegativity. Therefore, chlorine, bromine, and iodine molecules are nonpolar. That means that the only kind of force that's available to them would be London dispersion forces. Now it's interesting, chlorine exists as a gas. Bromine exists as a liquid. Yes, it's highly volatile. It vaporizes rather easily, but it is a liquid. Iodine presents itself as a solid. It sublimes easily, but it is a solid. Remember that we said that the physical state of a substance is an indicator of the strength of its molecular forces. So iodine being a solid must have stronger intermolecular forces than bromine, which in turn must have stronger intermolecular forces than chlorine. But remember, the only forces that are available to these three molecules are London dispersion forces, which simply have to do with the distortions in the electron clouds. But remember, as you go down a group in the periodic table, let's say from chlorine to bromine to iodine, remember, the sizes of the atoms increases. And therefore, we expect that the molecules formed by these elements also increase in size as you go from chlorine to bromine to iodine. In other words, what we're saying is that as these atoms get bigger, the larger these electron clouds, the more likely they are to be distorted. And therefore, the more likely that you'll have these temporary dipoles that generate London dispersion forces. So the mantra here, the lesson to take home is that larger atoms and molecules will have stronger London dispersion forces. Remember, to get London dispersion forces, there has to be a distortion of the electron clouds around the molecules and the ability to induce temporary dipoles in your neighboring molecules. So there are two things, therefore, that the magnitude of this induced dipole is going to depend on. Number one, the polarizability of the electrons. Man, even I have a hard time pronouncing that. But what that means is what we just saw with chlorine, bromine, and iodine. The larger the molar mass, the more electrons. Therefore, the larger the electron clouds around the molecule, which means that it has an increased probability of being polarized. Yeah, I don't want to say the word because I can't pronounce it. And therefore, the stronger the London dispersion attraction. All right. The other factor is the shapes of the molecules. We'll have to visualize that in the next slide, but let me just explain what that means. The more opportunity you have for the molecules to interact each other, in other words, the more surface to surface contact you have, the larger the induced dipole. And the larger the induced dipole, the stronger the attraction between these, all right? So the more chance they had to interact with each other, the more likelihood that a temporary distortion in one electron cloud is going to induce a temporary dipole in the neighboring cloud. Let me show you with these two compounds here. On the left, we have something called N-pentane, and on the right, we have something called neopentane. Notice that both of these compounds have the same number of carbons and the same numbers of hydrogens. They are just organized in a different way. N-pentane is organized as a chain of carbons, and because of the tetrahedral geometry around each carbon, it looks like a zigzag kind of chain as opposed to a linear chain. The neopentane essentially has a central carbon around which are these carbons with their entourages of 3 hydrogens each, organized in a tetrahedral shape. So if we kind of like add up the electron clouds, you can see where the N-pentane looks more like a distended electron cloud, kind of like a little mini sausage, perhaps, on the left, whereas the neopentane electron cloud would approximate a spherical shape. Notice that when you bring together the spherical shapes of the neopentane here on the right, their point of contact is very, very small. It's a very small surface contact area. Whereas in the case of the N-pentane, when they approach each other because of the shape of those electron clouds, there is a larger area for interaction here on the left. And you can see how that will generate a much stronger type of intermolecular London dispersion force. Okay, so let's take a little time to practice here. I'm going to give you here 3 different compounds, and I want you to think what types of intermolecular forces exist between each of the following molecules. Remember, we have so far 2 candidates, London dispersion forces and dipole-dipole forces. And I took the liberty of drawing there the SO2 structure for you. You may have an older version that has the one of the resonance structures that has one OS double bond and one SO single bond. But you can draw it this way also to minimize formal charges. The shape is still going to be the same. All right, so let's think about this. When you look at H and Br, that is a single covalent bond. You have to ask yourself, is it polar or is it non-polar? Well, you have to go back to your periodic table that has those electronegativity values. Bromine is 2.8, hydrogen is 2.1. So that means that that covalent bond is polar, has a difference of greater than 0.4. So it should be able to do, right, dipole-dipole forces, right? But remember, just like with any other compound, there are also dispersion forces. Okay, dispersion forces are not exclusive. They happen with every kind of molecule. Dipole-dipole forces are exclusive. They only happen with polar molecules. Okay, let's look at the next one. CH4, you remember our good friend methane, right? It has that shape there, tetrahedral shape. So what do you guys think? Is it polar? Is it non-polar? Would it have dipole-dipole forces or only dispersion forces? Okay, remember that I gave you a little shortcut, which was to ask, number one, are there any polar covalent bonds in here? For all practical purposes, the difference in electronegativity between C and H is 0.4 or less, which means that we don't consider those bonds to be polar. And therefore, this is a nonpolar molecule. So dispersion forces only. Okay, let's look at the next one, sulfur dioxide. Let's look at the structure, look at the shape. Ask yourself, number one, is there at least one polar bond in here? Well, the answer is yes. Remember, the sulfur oxygen bonds are polar. The dipole is going to point towards the oxygen atoms. And because this molecule is not symmetric, that lone pair over there on the top, and the bent shape causes those two dipoles to add up. All right, so this is a polar molecule. So it'll have dipole-dipole forces. And of course, there will be also dispersion forces involved in here. Okay, excellent. So what we're going to do now is we're going to take a break before we tackle our next topic, which is the properties of liquids. Let's take a quick 10-minute break here. And when you come back, please be ready. We're going to study the properties of liquids, and we're going to see how intermolecular forces can help us both predict and explain some of the macroscopic properties of liquids. All right. So we're going to take a break here, and I will see you in 10 minutes. So we'll reconvene, let's say at 2 p.m. All right. Be back at 2 p.m. Thank you so much.